Hello, this time we're going to discuss a solution to a matrix equation that involves the product of matrices. So, first thing, well, we have this matrix. I'm going to describe it in terms of rows. So 1, 2, 3, 6 multiplied against xz yw should be equal to the zero matrix of the 2 by 2 zero matrix. But what can we do with this? Well, there's not much that we can do. I'm going to actually perform the multiplication. And thus, we obtain the following equation. Remember, we have to multiply the first row against the first column to obtain the entry 1, 1 in the matrix. So I have 1 times x plus 2 times y. And similarly, I have 1 times z plus 2 times w, and for the entry 1, 2. And now the entry 2, 1, 3 times x plus 6 times y. And finally, the entry 2, 2, second row, second column, which is obtained by multiplying the second row, against the second column. So that should be 3 times c plus 6 times w. And all of those, well, all that should be equal to 0, 0, 0, 0. Now, matrix equality is obtained entry by entry. So this matrix equation induces 4 linear equations. Which ones are those? Well, the first one is that says x plus 2y is 0, c plus 2w is 0, 3x plus 6y is 0, and 3c plus 6w is 0 as well. We may organize this by listing them as 1, 2, 3, 4. 4 equations, 4 unknowns. Well, let's introduce an augmented matrix for this object. 1, 2, 3, 4, indicating the equations. X, Y, Z, W, and the constants, right? As we have done it before. So we have 1, 2, 0, 0, 3, 6, 0, 0, 0, 0, 1, 2, 0, 0, 3, 6, 0, 0, 0, 0. So we have codified the equations in this 4 by 5 matrix, right? But then look, we have copies of this matrix that I'm circling here, right? What this says is that in the row reduction process that I'm about to perform, I will have very similar operations. In fact, look, when I perform the elimination process on the first column, I have row 2 minus 3 times row 1. I can obtain essentially the same type of operation to use this as a pivot and then eliminate this entry on the third column. And that can be codified in this elementary row operation. To row number 4, subtract 3 times row number 3. And then, well, of course, you obtain the following matrix. 1, 2, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 2, 0, 0. Is this in row reduced echelon form? Well, of course not, right? As we have this row of zeros not at the right position. But that's not so relevant, because from here, look, what we obtain is the following system of equations. The one that says that x plus 2y is equal to 0, from this row, from the first row, and another equation that states that z plus 2w is equal to 0. Well, I think we can do better. I think we can organize this system of equations in a different way. Instead of using this 4 by 5 matrix, I think we can codify everything in a 2 by 4. How so? Well, first, note the redundancy that we have here, right? There's a bunch of zeros, and we have copies of the matrices here. So what we're going to do is simply condense the information into the following. We have 1, 2, 3, 6. Extend 0, 0, 0, 0. You may say, hey, wait, what's going on? Well, whatever equation we have associated with the first should be obtained from this entry. The other one, the second, obtained from here. The third from here, and the fourth one from here. And now, instead of performing two operations just as we did above, we're going to perform one, row number 3 minus 3, row number 1. Well, 2, the second row, I'm sorry. And thus we obtain this 1, 2, 0, 0, 0, 0, 0, 0. Remembering what we were doing before. Whatever we have here is associated with equation 1. This one with equation 2. Sorry, there's a mistake here. This should be 2 and 3. This one with equation 3. And this one with equation 4. In other words, we read it. X plus 2y is equal to 0. 0, x plus 0, y is equal to 0. 1, 2, 3. We have z plus 2w is equal to 0. And finally, equation 4, we have 0 times z plus 0 times w is 0. Now we can perform this reduction, right? This compression based on the structure of the matrix product, right? That we were developing. Now let's continue, because this says, well, that x is equal to negative 2y and that z is equal to negative 2w. So from here we get that a solution x, y, z, w, well, actually looks like this. Negative 2y minus 2w, y, w, which in turn I can decompose as y times negative 2, 1, 0, 0, plus w times 0, 0, negative 2, 1. And with this, we found a parametric solution to this equation. And well, as you can see, it's not absolutely necessary that we use all the data that we are given, as some of it may be redundant and can be expressed much more efficiently. I hope that you like it. Take care and subscribe.